Have you ever wondered what everything around us is made of? Around 2,500 years ago, Democritus did. He was a Greek philosopher and he wanted to check how small he could cut any object until after which he can't cut it anymore. He cut the objects into such minute pieces, he called them atomos. Atomos is the Greek word for uncuttable. Fast forward to the 1700s, and scientists discover that all objects are made out of matter, which in turn is made of extremely small particles called atoms. You, I, a chair, and even rocks are made out of atoms too. A fun fact is that oxygen is the element with the highest concentration in our bodies. Combinations of one or more similar atoms makes up what we call compounds. In today's world, you might have heard about elements such as oxygen, carbon, and hydrogen. But do you know who discovered these elements? How on earth would they have even done that? How many such elements exist? Where are all these elements found? Is there a list that contains every element known to mankind? These are some of the questions that we will answer in today's episode of The History of Something. Today's episode will be divided up into 4 parts. The first part will talk about the early days of elements. The second will cover about the stories that some of us know, such as Lavoisier or Priestley. The third part will be covering what is today known as the periodic table and how exactly it came into existence. The last part will talk about the elements outside of our planet Earth that might be able to be found. This episode today is not inspired by the Value Tales, but I highly recommend for everyone to read the series. But enough of the introduction, let's jump right into the explosive story of the elements. In ancient times, around 450 BC, everyone, including some really smart scientists like Aristotle, Democritus, and even Plato, believed that matter was comprised of 4 elements: fire, water, air, and earth. They thought this because their main goal was to see how exactly the world worked, and these 4 elements were present throughout them. Therefore, they said, hey, these 4 must be the elements. The 4 elements are now known today as classical elements. They thought that additional things could be created through a combination of those 4. The main goal for most people was to make something valuable with these elements, which eventually led to alchemy, but we'll get to that when we get there. Surprisingly, it wasn't just the Greek who believed that there were those only 4 elements. As in most areas of the world, the theme of having 4 main elements persisted. In ancient India, for example, they had these 4 elements in addition to space. They were quite ahead of their curve in regards as no one else had really tried to quantify space as an element, but the Indians had. The same theme could be seen in ancient Japan and ancient China, with them having their 4 base elements, and one more that represented nothing or the unknown. In China's case, that took the deep space, while in Japan's, that took the deep, deep ocean that they didn't know about. Now, most people would have really cared really little about these elements if it wasn't for the concept of alchemy that made them quite popular. You see, people thought that they could make something really valuable with things that necessarily weren't very valuable of themselves. And a really common example of this is making gold, right, out of useless metals. This kind of concept morphed into the field of alchemy. Jabir ibn Hayyan was the first person to really write down this stuff about this new type of science, the study of making new things. He came up with a couple laws that kind of encompass the study of alchemy. I wrote over 100 books that were extremely detailed in the study of alchemy and its real purpose in the world. Furthermore, important to many were my theories of sulfur and mercury. I stipulated that all the metals in Earth could only be made with a combination of these 2 elements. Depending on the quality of the 2, different new elements were made. If both the sulfur and the mercury were really high quality, valuable metals such as like gold and silver would be made. Contrastingly, if they were low quality, much more low quality metals would be made. Not much more was done with alchemy until a scientist in the 1400s named Paracelsus came along. So Paracelsus was a Swiss scientist, and if any of you know about him, you probably know that he was the founder of the anatomy. He would take these remains of the human body and really analyze it. But not many people know that he was really critical to the field of alchemy and chemistry. Paracelsus invented chemical therapy, specifically chemical urinalysis, and suggested the biochemical theory of digestion. Again, he's basing all this off of his in-depth study of the human body. So he drew a lot of parallels to Jabir. However, he thought that mercury, sulfur, and salt, instead of making metals, were the cause of all diseases in the world. He thought that by having these three, all the diseases in the world would come up. He named these the Tria Prima. The Tria Prima also defined human identity. Salt represented the body, mercury represented the spirit and the imagination, sulfur represented the soul, your emotions and your desires. By understanding the chemical nature of the Tria Prima, any physician can discover the means of curing a disease. Now, around the same time when Paracelsus was conducting his experiments about having salt, mercury, and sulfur be the causes of all diseases, the tale of the Philosopher's Stone came about. The tale of the Philosopher's Stone is that this stone could touch anything and turn it into gold. This throughout the 1600s drove this heavy involvement in this field of alchemy, and a really, really special scientist talked about and really tried to hide his deep involvement in the field. And I'm talking about Newton. Most of us don't know that he was so invested in alchemy due to his part keeping it a secret. We all know that Newton involved in himself with optics and obviously like the discovery of gravity, but why would he keep alchemy a secret? You see, alchemy, the whole point of it was to create something valuable. And people thought that even if someone tried to create something valuable, they could kind of have like a target painted on their back, because other kings would try and capture that person to make riches for their kingdom. That is why, even though that Newton believed that alchemy would not work, he still tried so hard to make something even minutely more valuable than what he started with, and because of this, he created many, many compounds that we use today. Usually, scientific discoveries don't happen through a constant rate through history. There's often periods that we know as golden ages where a lot of new discoveries happen quite rapidly. Going into the early 1600s, not many elements were known. This all started with an influx of new discoveries led by Lavoisier and Joseph Priestley. Lavoisier is known for changing the course of chemistry as he changed the science from being qualitative to quantitative. Qualitative kind of is just the descriptions of an experiment. What color is it? How does it feel? But quantitative really puts numerical data points to it. It weighs so and so grams. He was the first one who really quantified these experiments, leading to the invention of stoichiometry, which is the balance and of chemistry, especially masses from one side of reaction to the other. He is quite important to us because he was the one who discovered oxygen. Until then, everyone knew that there was something in the air that made a flame burn, but no one really knew what that was. So, as a part of their experiment, an inverted glass cylinder was placed and burned a candle in it until it burnt out. So you can kind of picture it as the flame being my hand and the candle being on top of it. A mouse was then placed in that cylinder only to find out that the mouse died. It was therefore concluded that the same element in the air that causes the flame to burn is also necessary to sustain life. Through this, they coined the name oxygen for this element because that was the one that they were able to kind of isolate. There was another experiment where a green plant was placed in the cylinder after the candle burnt out. It was observed that over time, the air inside the cylinder was able to burn a candle or keep the mouse alive for a few hours. Lavoisier later called this oxygen. Afterwards, people turned to many other compounds or objects and tried to split them using electricity. Electricity was kind of a new concept that was discovered by Benjamin Franklin, and I think we all know about his famous kite and key experiment where he discovers that lightning in fact is electricity. And this is actually really important because a scientist named Volta creates the voltaic pile, which you can basically think about as the first concept of a battery. So this is really critical in discovering new elements because until then, people only knew how to either burn something, boil something, or maybe like break something into pieces. But using electricity, they could now really split it at that atomic level, which is what exactly is needed to try and discover or even find new elements. So this process of splitting something um, is called hydrolysis, and it's named after water because that was the first kind of way they did it. The first kind of scenario where electricity was used to split something was obviously water. And they just started after they split water into hydrogen and oxygen, they just started to split things one by one. So as I said, right, one of the first things that they decided to split was water, and then they also discovered the presence of hydrogen, the other gas. And that confirmed the presence that, oh, this gas named oxygen, which they already known existed. Other times they did this was like splitting other things such as like iron oxide. They split many types of rocks. They split many types of like paste just to see what exactly they could come up with. So obviously not all of their experiments or trials with hydrolysis were successful because you have to remember this is still a very much trial and error process. They're taking some sort of day-to-day object, for example water, and they're running this current through it to see what gases would be produced. So they obviously tried with many more things, but not all of them would yield elements. Some of them would be only broken up into smaller compounds, but that is something for another day. In the end, around the mid-1800s, like around 1850, the scientists had a pool of elements that they had collected. But now they had to figure out how exactly to organize them. And this is where the discovery, or really the invention, of the periodic table comes to play. So before we dive into how they organized all these atoms, we first have to step back and realize, or even think, what exactly is an atom? So throughout history, there have been many versions of what exactly an atom is. And we can first start off, obviously, with the Greeks, looking at Democritus, who we talked about much earlier. And his theory of an atom was just something really small. They didn't know exactly what it was. They just thought it was really small and it had like a certain property. Even then, that was flexible because, remember, they only knew the 4 elements. But they just thought something that you can't see with your eye. Following up into the late 1800s, there's this person named John Dalton. And John Dalton's model of an atom was basically like a really, really small ball, right? A really, really small sphere that had a certain property. Obviously, there was a really famous experiment which might be the subject of another episode called the Rutherford's experiment, where he disproved that. And then what happened was the plum pudding model, which I'm not going to get into too much detail, but it was kind of like a jelly substance around your nucleus of your atom that contained all the electrons. That also got disproven later, leading up to the Bohr model. Now, most of us might know what the Bohr model is because in many scientific journals, we see our atom with the small, like the electrons looping around it. And that used to be the standard for a really long time until now, which is the atomic cloud, where there's not exactly these electron orbitals. There is more of, it's just a cloud of electrons. And just to make sure for anyone who doesn't know what, how an atom is, there are neutrons and protons that make up kind of like the nucleus, and then on the outside we have all these negatively charged electrons. And all of these, in a way, kind of tell us what the element is and the properties of that element. So now that we know kind of what an atom is and how it kind of works, let's talk about how someone would even go about organizing this. So finally, in 1869, a Russian scientist named Dmitry Mendeleev proposed a framework that became the modern periodic table. He first organized the elements based on their masses and chemical properties and left gaps for elements yet to be discovered. So some of the chemical properties that you might think about, that he would have thought about, was, are they flammable? Are are some of these toxic, are some of these gases, and he organized them into kind of families. So while he was arranging the elements according to their atomic weight, which was their mass, he found that if they did not fit into the group he would have to arrange them. By doing so, he had to make new groups for each when a family was kind of full. At that point, he knew that there were 66 elements that he could fill in, and for the gaps, like we talked about, he predicted the properties of some of the undiscovered elements, and he gave them a name. He would put EKA before an element that they knew, and then they would say, oh, this is similar to aluminum. So, for example, there was an element called EKA aluminum that shared many of the properties of aluminum, but that later was discovered to be gallium. So the term periodic reflects the fact that these elements show patterns in their chemical properties in certain regular intervals. So basically there's a pattern that repeats over the periodic table. The periodic table is one of the most powerful icons in science. There's a single document that consolidates much of our knowledge in chemistry. UNESCO named 2019 the International Year of the Periodic Table to mark the 150th anniversary of Mendeleev's publication. Mendeleev's periodic table has now expanded to 118 elements and looks something like this. From left to right, the elements are lined up in rows based on their atomic number, the number of protons in the nucleus, and some columns are skipped in order for elements with the same number of valence electrons to be lined up on the same columns. Valence electrons is basically the outermost number of electrons in an atom's shell. When they get lined up this way, as Mendeleev discovered, elements in the columns have similar properties. Each horizontal row in the table is a period. There are 7 or 8 total periods. The first one is short and only has 2 elements, hydrogen and helium. The 6th period has 32 elements. In each period, the leftmost element has 1 electron in its outer shell, and the rightmost element has a full shell. So just to reemphasize, a shell is just the number of electrons that it has orbiting the nucleus, and it gets a bit more complicated, but basically the valence are the electrons at the end. So now groups are the columns of the periodic table. There are 18 columns of groups, and each group has a different property. For example, the group on your the rightmost group is called the noble group, and it has inert gases such as helium, neon, and xenon, and those don't really like to partake in any chemical reactions. So as I said, these elements line up on the 18th column of the periodic table, and they have a full outer shell of electrons. So if you see at the bottom of the periodic table, there are kind of 2 separate lines. It's almost as if we took something from the middle and we put it at the bottom. This is because all of these elements fit in the same group as lanthanum, which is a group 3, and they have all the same properties. And the second is the actinide series, and they also fit in group 3 along with actinium. So this lining up and grouping of similar elements helps chemists when working with elements. They can understand and predict how might an element react or behave in a certain situation. Do you know that carbon, the black stuff we see when there's a fire, sitting in row 2, column 14 of the table, is critical for life and can make more than 10 million compounds? While francium, the element which is number 87, is the rarest element on Earth and is highly radioactive. At any given time, there's only a few ounces of elements on the Earth. Finally, element oganesson, atomic number 118, is the latest element discovered by the Russia-American collaboration. Now, you might be thinking, we can keep on discovering elements forever, right? Well, no. The upper bound that science suggests that we could do at this point is 149 protons. At this point, science suggests that the nucleus of your atom would become so unstable, the whole atomic shape would not be able to form. So you might ask yourself, what if we explore other planets? Wouldn't that be something to think about? A whole new set of elements or new compounds with interesting and strange properties? we can safely say that there's not going to be any more elements discovered until 118 because the rules of chemistry dictate that. However, it is really possible that we find new compounds with properties that can help us in the future. It could be one of you who discovers these new compounds and finds out how to use them to help benefit our society. By doing so, you would do a great deed, but also continue to write the story of the elements and their history.